All right, let's get started. I'm gonna turn the lights off here in the front of the room because we're gonna be looking at some stuff. What you got? Oh, chair. Do you want to sit on a chair today? You sure? Okay, let's. Oh, did that? I'm sorry. Let me put the magnet thing there. Yeah. You got it? Thank you. Okay, so mini exam 1 is due on Wednesday, beginning of class. You'll bring it up here, you'll set it on my desk. Stapled, in order, everything right, like I said. I'm also asking that if you worked with classmates, this is new, I didn't put this in the instructions, but if you did work with some of your classmates, you know, have your name and then somewhere up there just say, you know, I worked with so-and-so, just so that there's full disclosure, right? On the second mini exam, you're not supposed to work together, right? Yep. So I'm going to be very cautious, or not cautious, I'm going to be paying attention to your work because it's very unusual for two people to have the same work, right? They may get the same answer, but the work is probably going to be different, the approach. So we'll talk more about that later. Any questions on those? Yes?
Do you want us to staple the exam that you gave us or just our paper?
I don't need the exam, but you can make that your first page if you want. Yes?
Do we have to write out the problems on the exam on the actual
Nope.
work? Okay.
Nope. And yeah, just to have it in order. That's the main thing. I don't want to be going from like number 5 to number 1, then back and forth. Yes?
Could we, could it be printed out?
I don't care if you type it up somehow and then print it out. That's fine as long as it's legible and it's your work.
Well,
That's the only thing.
It would be hard to turn in work on a whiteboard down here. So I wanted to do it there.
Yeah, if you're doing it like electronically. Oh, are you just like taking pictures of a whiteboard?
Yeah, take a picture of a whiteboard.
As long as it's legible.
Cool.
It just needs to be legible.
That works.
Anything else?
More legible that way.
Okay, now, I know some of you have waited to the end, and that you might be able to get by with this mini exam, but I'm afraid that might catch up to you if you, like the one I gave you last week, if you wait till 2 days before, it's probably not going to happen, So just be aware, the expectation is that you're working on these as we go.
When did the next ones due? Week after next?
2 weeks from today, I believe.
Okay.
I don't remember the exact date that I put on there. 15? Yeah. Check the exam. All right, so today we are going to talk about Chapter 10, Section 6. This section is very visual, all right? And so I'm going to be doing a lot of talking and explaining. We're not going to be doing a ton of problems until we get to the very end, and then we're going to do a few little examples, and we'll move on. The main takeaway here, am I recording? I don't remember hitting the record button. I did. Okay. So the main takeaway for this section is for you to be comfortable with the idea of surfaces in three-dimensional space, and that each of these surfaces has an equation that goes with it, and we need to be able to somehow match the equation with what type of surface it is. So this is just going to be a bunch of explanations as what things look like. So I'm going to take us back to two-dimensional space, and we're looking at the equation x squared plus y squared equals r squared. Here r is a constant, so imagine r is just a number, right? So that's the equation of a circle that's centered at the origin. This should be very familiar to us, right? In two-dimensional space, that equation generates a circle, which you could say is a curve, right? That's a curve in two-dimensional space. Now, if we tweak that equation just a little bit, and instead of having it, x squared plus y squared equals r squared, if we divide the x squared term and the y squared term by numbers, I'll give you a specific example next to this. If we were to take, let's say x squared over 4 plus y squared over 9 equals 1, this is no longer going to be a circle. we're going to get an ellipse. All right, so if I change the value of a and b, you can see what happens. So this is me changing the number underneath the x squared. I'm making it bigger, okay? I just made it bigger, and what it does is it takes basically a circle and just stretches it out in one direction. And then if I do the b, which is the number under the y squared, it's going to stretch it the other way. Right, like that. So we get an ellipse, which again is a curve in two-dimensional space, right? Then we take that equation right there, we tweak it a little bit more and change that plus to a minus, and we no longer get an ellipse, we get a hyperbola. So this is what a hyperbola looks like. It's almost like two parabolas coming together, kind of. Not really, they're not parabolas, but they're called hyperbolas. All right, so what this first beginning part is trying to show you is how these generic equations that we have are all very similar to one another, but a simple change, oops, that's an a simple change in just a sign here or a sign there, right? If I change this from a plus to a minus, it's going to change the graph, right? So it's just us noticing how those little subtle changes change the picture. And now what we want to do is we want to extend all these ideas into three-dimensional space. Okay, so now we're stepping off the flat sheet of paper out into space, and we're saying, what do things like this, equations in three-dimensional space look like? So we're going to start here with this reminder that in three-dimensional space, equations that we have here will involve the three variables x, y, and z. Those are the three variables that we should see, right, for the x, y, and z axis. So when we have an equation that has those three variables involved, we should expect to see surfaces, not curves. Right? So we should see some surface in three-dimensional space as opposed to a curve. The next section is about curves in three-dimensional space, but we're starting with surfaces, which is kind of weird. It seems like a curve would be easier, but just bear with me. Let's just keep going. All right, so before computers, right, to sketch a surface in three-dimensional space was somewhat challenging. You had to do these things called traces, and I'm going to give you an example of how to do a trace, and then after that we're just going to kind of wave our hands at it a little bit and be like, hey, but we have technology. It's easy for us to go just type it into, well, I showed you at the beginning of class, we have GeoGebra, I believe was the website. I'll take you back there again. I can show you how to type it in. All right, so here's our first one. All of the things we're about to study are called the name of the section, where is it up here? Let me go up here to the beginning. The name of this section is cylinders and quadratic surfaces. All right, so the first of these type that we're going to talk about is this equation right here. X squared plus y squared equals c squared. Now, that looks a whole lot like this first one here, right? X squared plus y squared is r squared, except I'm using c instead of r, right? So it's the equation of a circle that we had before, right? Where you have x is being squared, the variable x and the y, they're being added, and then we have equals a number squared. And there's no z in the equation, right? So if I were going to go to try and sketch this old school, before there were computers, right? Here's what I would do. Let's act like we don't have that picture there. I'd say, all right, let me take a specific example. In R3, so I'm going to state here that I'm in three-dimensional space. I'm going to take x squared plus y squared equals, let's go with 4. Okay, so we know in two-dimensional space that's a circle, right, centered at the origin, radius of 2. What we have now is that same circle, right, that same circle here, x, right, y, z. We have that same circle, but this is the ground, right? This xy plane is now like the sheet of paper. So we have that circle there, right? But our z, our up and down, can be anything we want it to be, right? So when I do this, I need to fix some z. So I'm going to say let z, I don't know, I'm just going to go with 0. If z is 0, then what I have is that circle on this xy plane, right? So I have that circle. So if I were to go try and draw this, I would draw what is called my first trace. And this is, again, this is where it's hard, because you're trying to draw on a flat sheet of paper, you're trying to draw three-dimensional space. So I try and draw my little circle down here, right? And that's living on the xy plane. And this is the equation x squared plus y squared equals 4, with z being 0, right? And it's hitting here at 2, right? Because that's where it hits, the radius is 2. And that would be my first trace. And now what I do is I change the value of z. So I'm going to do the same thing, but this time, what do you say we raise z up to 1? And then it's going to draw that same circle, isn't it? It's just now moved up 1. So if I now do let z be 1, then it's all the points that satisfy that equation, which is the circle, but z coordinates are now 1, so now it looks like, I don't know, I'm going to exaggerate it. It's like up here now, right? It's been raised up. And then I could say z is 2 and move it up again, right? And move it up and keep moving it up, right? So if I were to put all these traces together, oops. I can imagine that what I'm doing is intersecting a cylinder, right, with a plane, the xy plane. I'm intersecting it. Where am I? Oh, I'm not. There it is. Hold on. Where the heck is it? All right, so if you can see, I'm kind of like intersecting. If I had all these traces, I'm imagining that what I'm doing is this right here, z equals 0, is a plane. And I'm cutting through my surface, and I'm getting that circle. And then I move that plane up to z equals 1. I cut through, and I get a circle. All those circles together, right, create that cylinder. What else? What if I change my plane? Instead of doing that plane, I do, where am I, linear trace? There we go. Planes that are cutting through this way, right? Then look at what happens. I hit the cylinder in a line, right? So if I cut the cylinder one way, I get circles, but if I cut it the other way, I get lines. So you could describe a cylinder as a surface where the intersections are either circles or lines. And that's what I have written down up here, right? A cylinder is something that when you do the traces, you get circles and lines. Any questions? Yes?
Is it like two parallel lines, or is it like a square?
No, so for the ease of me writing the code for this, I did both planes at the same time. So imagine the back plane's not there, and just take this first front plane. It would cut through that cylinder in two lines that are parallel to one another. Okay, now in this equation, notice that the z does not appear in the equation, right? The z does not appear here. So we would say that z is free. And so what I think of when I think of this type of cylinder is that if I have x squared plus y squared equals a constant, I'm going to get a cylinder, right? And it will open, I say opens up, it opens up through the z-axis because z is not there, right? Z is not in the equation. What would happen if I change it to x squared plus z squared equals, let's say, a constant squared? So now you're going to get a cylinder, but your circles live in what plane? The xz plane. So let's see, here's x, right? Here's z. So my circles are this way this time, right? Instead of being the xy plane, my circles are no longer here. They're like this. And then what I'm doing is, what variable's not here?
Y.
The y. So here's my y-axis. So I have these circles like this, and I keep on moving my y's. So I move these circles out this way and out this way. So I get a cylinder going like that, right? Which is not that one. Yeah, there we go. So remember, the green axis. This is the green axis. We said it would come out this way and go out that way, right? So that's what an equation of a cylinder looks like. Well, that's the equation of it, and that's what it looks like visually. And then the last possibility we could have here is to have this, right? That again would be a cylinder that would have circles in the YZ plane. So now Y and Z, right? So circles go this way, and they go down the x-axis like this. And that would be our last picture right there. See the x-axis, cylinders coming down that way. So whatever variable is not there is the axis the cylinder goes down. You got it? Okay. Now, let's move on. The next type. The next type is called a parabolic cylinder. And the traces are parabolas and lines. So it's like when I cut it this way, or I cut it this way, or I cut it this way, I should expect to see parabolas and lines. So here it is. That's a parabolic cylinder. It's kind of weird that they call that a cylinder, right? But it's called a parabolic cylinder. And so if I try and cut through here, oops. There we go. There we go. So see, if I cut through, I get parabolas that way. And then if I try and cut through the other direction that way, let me take the parabolic ones out. Can you all see that? If I cut through with planes that either go this way or that way, I'm getting lines. Yeah? So you get parabolas and lines depending on the plane. Now let's look at the equation. Z equals a constant times x squared. Z equals a constant times x squared. So what variable is not here? The y, right? And notice that it looks like, if you look at it from here, let me get all this crap out of here. Don't even need that. If we look at it like this, it just looks like a parabola, right? And I'm looking down which axis? I've got the red axis and blue axis. So it's like I'm looking at it from here, right? And I see a parabola where I have, this is my y-axis, so y and then z. You got your parabolas like this. And then as you move your x values, your traces, you go out this way, you move all those parabolas down this way and down that way. Is this all making sense?
Mm-hmm.
Yes?
Are these surfaces like volumeless and it's just surface area?
Yeah, it's just surfaces, so we just talk about surface area. Now, we could project that down to the xy plane and talk about a volume. We will do that later. But for now, we just want to, if we get an equation later, do we have any idea what this looks like, right? Yes?
With one of these, if you were wanting to make it like an actual 3D object that doesn't stretch infinitely, would you just add domain restrictions, or
Yeah.
is there a modification to the
Yeah, it would be like if you wanted this one right here, this example right here is like z equals, let's just make it real simple, z equals x squared, right, like that. That would go down this way and down that way forever. So if I wanted to restrict it, what I could do is I could put something like y between two values, let's say 0 to 2. And then, yeah, that's my x, so my y would only go out from 0 to 2, so you'd only have this parabola right here. The parabolic cylinder would only go right here.
So that's all you do to...
Yeah, to restrict it.
domain restrictions.
Mm-hmm. Okay, we're not going to do the traces by hand, okay? It's just a pain. And then now if you do the same equation, z equals x squared, c x squared, now your y is free. Wait, was that the one we just did? Hold on. Yeah, oh, I meant to do this one right here. So if we do z equals c times y squared, now your x is free. So I should expect parabolas like this going out the x direction both ways. And then I could, there's how many of these? 6 of them, right? Because you only need 2 variables to appear at one time. So we have this right here, look, x and y squared.
Yep.
So that's, let's see, x is y squared. So now you've got the x-axis, y-axis, right? And then your z is free, so it goes up and down like that. So it looks like this. And then we could do this one where you have x and z, but your y is free. Notice that these have switched places. In the first example, it was z equals x squared, like that. So it's going to be a different looking shape. We don't need to, I'm not going to give you a test where you have to know all these and memorize them. At the end of the section, actually in the ebook, there's a page in the ebook that has like a summary of all of this. So that's a good reference to go back and look at. All right, let's move on to the next type. Next one, ellipsoid. An ellipsoid. An ellipsoid is basically like an egg, and all traces are ellipses. So no matter how you take this surface, if you cut it with something like the xy plane, or like z equals 0, or x equals 0, y equals 0, no matter how you cut it, you're going to get ellipses. So do y'all see I've already put the trace curves on there so you can see there are a bunch of ellipses on there? And then, let me see. That's me hitting it with the plane going up and down. Those are all ellipses. If I hit it with the plane the other way like this, let me show you the actual trace. There they are. Do you see all those are ellipses as well? And if I do it with the plane like this, those are ellipses as well. So it doesn't matter as long as you're doing something that is parallel to these plane, to the xy plane, xz plane, yz plane, then you should get ellipses. Notice these planes I'm hitting with aren't like tilted or anything, right? They're parallel to the coordinate planes. All right, what's the equation look like? Hold on, let me just put this up here. Here's the equation, right? That's the equation of an ellipsoid. Notice all three variables are here, right? All three variables, x, y, and z are all there. Is this the first one that we've had that has all of them? This is, right? This is, yes.
What is the one supposed to represent since the radius isn't ever changing?
Well, that's what makes it not a sphere, right? So like the equation of a sphere we've already studied.
It's just stating that it's not a sphere.
That's right. It's not, sorry, this side should be r squared. That's the equation of a sphere, right? That's actually the first surface we ever studied. We studied it earlier, right? Now we know that equation. This equation is different in the sense that we have numbers underneath. This is just like the ellipse versus the circle, right? The ellipse versus the circle. Sorry, the circle versus the ellipse. It's kind of this in three-dimensional space now. So we have all three variables being squared divided by numbers equals 1. Yes, sir?
Can you reasonably explain the fact that that's a 1 instead of a r? In that the way you would acquire that effectively is you would divide both sides by your r?
Well, if you take this equation and you divide everything by r squared, right? Then they all get divided by r squared. R squared equals 1. Everyone see that? If I did that, then you would have an ellipsoid that is the same stretch in every direction, which makes it a sphere, right? So that's what would happen if you took the original sphere equation and divided through. But we make a distinction.
Yes.
We don't call a sphere an ellipsoid. For an ellipsoid, we assume that you cannot divide, that the numbers underneath here are not all the same.
Does the radius in one direction, radius in the other?
You could look at it like a radius in one direction, the other in the other. Okay, so what are we looking for an ellipsoid? All three variables, right? All of them squared, and then they're all added together and equal to 1. That's what makes an ellipsoid.
Oh.
Now the next one, elliptic paraboloid. Let's look at the equation first. Do all three variables appear?
Yes.
Yes. Are they all squared?
No.
No, right? So not only are they not all squared, two of them are on one side being added together and the other one's on the other side, right? Just being divided by some number. If we ever have this scenario, then we should expect to see this elliptic paraboloid. Okay, so it's like a bowl, right? It's like a bowl. And do you see that that bowl in this picture kind of opens up through the z-axis, right? It opens up. Notice that z is the variable that's by itself and not being squared. That's what indicates which way this bowl opens. So let me show you another example below this. Look at this one. X squared over some number squared plus z squared over some number squared equals y. See, y is the variable on the other side this time. It's not squared. And so see that bowl goes out the y-axis? Yes?
What was the previous shape called again? Sorry.
Which one? The ellipsoid? This is all the same thing.
Oh, yeah.
Yeah, we're still in the same one, sorry, elliptic paraboloid.
Okay.
I'll let you know when we switch to another one.
All right.
So this is an elliptic paraboloid. This is an elliptic paraboloid, right? Sorry. That one is. That one, right? That's a bowl that opens up. A bowl that opens out the y-axis. A bowl that opens out the x-axis. Yeah?
So if you wanted to open onto like, you know, the negative x-axis, would you just make that x a negative number?
Yes.
Okay.
Yep. Well, you couldn't, if you make this negative, right? If I just change that to a negative, this would not have any solution. There would be no solutions.
Make my constant c negative.
Still can't work because this side would be, are you saying this number?
Yeah, whatever that number is in there, make that a negative number.
Which would be the same as changing the signs over here, right?
Yeah.
Yes.
So for the traces of the ellipse, like whatever.
Yeah.
Are they of like the same, I guess, coefficients? Like the same parabola, just like shifted up?
Yeah, well, it's not the same parabola. Let me do a trace on this one, just so you can see it, okay? And can we do the bowl that opens up? Because I think it'll be the easiest one to do, this one, yeah? Okay, let me give you a specific example of what a trace would look like here, or how we would do a trace. Let's do x squared over 4 plus y squared over 9 equals, let's just go z, all right? Z over 1. All right, that, if I were given that and I were asked, hey, what is that? I would look, I say, okay, all three variables are there. The x and the y are both squared. They're being added together. The other side is the z, so it's a bowl. It should open up the z-axis. I mean, you shouldn't know, I'm not expecting you to know it that quickly, right? But I could kind of look back at my notes and figure this out. Got it? Now, to do a trace, here's what I could do. Let's let z be 0. So what I'm doing is I'm cutting through, okay, remember I got this bowl, it opens up. What I'm doing, cutting through with z equals 0 with the xy plane. What should I expect to have there? Let's see, replace z with 0. All right, now multiply both sides by 36 to clear the fractions. And you get x squared plus y squared is what? X squared plus y squared is 0. So you could look at this as being a circle, right, with a radius of 0, which is a point. So it's the origin, isn't it? That's the bottom of the bowl. Now what I do is I change and I go, let's go z equals 1. So now I'm going to move the whole thing up 1 and slice, see what I get. If I do that, that is an ellipse, right? That's an ellipse. So whatever that ellipse is, I would draw it. Now, the next one will be a different ellipse, because if I change z to, let's say, 2 now, what's going to happen here? I get x squared plus 4, over 4 plus y squared over 9 equals, I'm replacing the z this time with 2, right? This is an ellipse, but I need to make that a 1, right? So I would divide here by 2. This would become an 8, and that would become an 18. And that's a different ellipse. Do you see? So I'd have a different, when I move up, I'll have a different ellipse, and then move up again, different ellipse. Yes?
Is the constant, like in the equation, z over a constant c? Are we assuming that's 1?
I did, because I'm giving you a specific example. Yeah. It could be different, yes.
It
Yes.
would be the same ellipse, but it'd be some scaled of some other ellipse, right?
It's all of those, right? It's that whole family of ellipses right there. Yeah. Yes, sir?
So the numbers that you're asking your y are being divided by are effectively deciding how wide
Oh, yeah.
the girth of the ellipse is.
Yeah.
What's the c doing?
Scaling it.
Is that scaling it like vertically? Well, like what does that actually affect?
Scales everything.
Oh, okay, the whole thing?
Yeah, the whole thing.
Shifts?
Yeah,
Okay.
the whole, it's in every direction it gets scaled.
Interesting.
Yeah.
Gotcha.
All right, so we've got that now. Let's see, here's the bowl again, then the bowl. Okay, now the next one.
Oh,
Hyperbolic paraboloids. Okay, hyperbolic paraboloids. This is, let's look at the equation. All three variables, right? Two of them are squared, one of them's not. Hey, this is just like the one we just looked at, right? Except we have subtraction instead of addition. Oof, right? And look at what it is. It's cool looking. It's like a saddle kind of, I don't know. You know. So that's it. We're not going to get too caught up with, you know, how you're going to, I'm not going to ask you to graph these, okay, by hand. It's just to show you it's a different shape, right? By a simple change of a minus here, we get a different shape. I'll show you another one, another variation of this. All three variables, two of them are being squared. We have subtraction between them. This one's by itself. And the saddle looks different, doesn't it? It kind of goes a different direction. That one kind of, I could kind of say it kind of comes out at us this way. I don't know. And then on that one, it kind of went up. I don't know. It's kind of hard to say what's going on here. If you look at it from the top, you get hyperbolas, right? What does it say? Hyperbolas and parabolas are what we should see. All right, let's move on to the next shape, a cone. All right, so cone, look at the equation here. All three variables, all three of them are squared. Two of them are being added together and the other one is on the other side, right? So doesn't this look a lot like, doesn't it look like this? We did that a minute ago, didn't we? And what was that? That was a,
ellipsoid?
that's an ellipsoid. That's an egg, okay? So we have an egg here, yeah? So that is not this. And what we would need to see, what you need to see here is that, obviously if I move that to the other side, it's negative, right? So, and then this one couldn't be here. It would need to be like a 0. So if I do this, that is a cone, right? Y'all see that? If I just move that to the other side, you've got your cone. Mm-hmm.
It also looks kind of like the Pythagoras theorem.
Yeah. If all these were 1, right?
Yeah.
If all these were 1. All right, notice that the variable that's alone by itself on one side of the equation, would y'all agree that I could say that's kind of the axis that the cone goes down? Like this cone goes like this and like that because the z is isolated, or the z squared. If I change it and I do x squared and z squared on this side added together and put it equal to the y squared on this side, then my cone goes down the y-axis, like this way and this way. And then I could do another one down the